noticed that they're in Calgary right now.
Fair enough. We'll make sure we record it.
Awesome.
Okay, yesterday we talked about two famous scientists. Did I talk with you guys about the idea that when you are a famous scientist, you get to name stuff after yourself? No? So, or after your favorite science teacher in high school? The Shulk, yeah. Be the new unit of dark matter or something. So, okay, so Boyle's law. Basically, Boyle discovered that if you increase or decrease the pressure, it correspondingly increases or decreases the volume. Okay. So the basic idea is that if the pressure were to go up, what does that mean happens to the volume? It would have to go down. Okay. How do you increase pressure? You squish everything in. Right? If you squish everything in volume-wise, so there's less volume, it means there's more pressure. Why? Well, let's talk about what pressure is. Pressure is really force over area. Now the area, let's assume the area is not really the relevant part here, it's not changing much. Let's talk about force. What are forces? Well, from grade 10, a force is like a push or a pull. Nothing's really pulling here, but is there stuff pushing? Sure. All of the molecules inside whatever you're talking about, like you have a box, I don't care, balloon, a tire, a underinflated Patriots football, I don't care. There are molecules inside, okay? And these molecules are moving. Why are they moving? Well, gases have translational motion abilities. They're able to actually move themselves all over the place. Solids can't. Liquids can rotate, but gas molecules can literally move wherever they want. There's actually a whole branch of chemistry that I wish I'd taken more of. It's called, basically the term is called entropy. I don't need you guys to know that. But entropy describes the randomness of particles as they move. Because these particles are going to move. The question is, well, where are they going to move? And so they move randomly. And so there's actually a study about that. The term is called entropy, if you care. Anyways, these particles are all moving. As they're moving, they're going to hit the sides of the walls. If they hit, that's like a push. A push is a force. More force means there's pressure. Well, now let's say we decrease the volume. So all of these particles are now in a box that are now this size. So I gave you guys the analogy of let's take all of us and shove us all in the closet. There's still 20 of us, but it's a little squishy. Currently, you're not really hitting each other all that much, but if we're all in the closet, we're totally going to run into each other a lot. It's going to be squishy, right? So it's not that there's more pressure because there's more stuff, and it's not that there's more pressure because we're moving faster, because we're still all, it's still 10 o'clock in the morning, we're still waking up, we're not all buzzed up as though we just drank energy drinks. Right? But because there's less room now we're going to hit the sides of the wall more, so therefore because we hit the walls more, there's more pressure. Does that make sense? Cool. Okay, Charles had a similar but different theory. His is about temperature. So you have two different boxes and you put a whole bunch of molecules inside of them. And this one is at 25 degrees Celsius, which is 298 Kelvin. And let's say this one is at, like, say, negative 200 degrees Celsius. What would that be in Kelvin? Yeah, you add 273, so this would be like, say, 73 Kelvin. This is pretty cold, eh? And this is like room temperature. Well, these molecules, yeah, they're going to move. They're going to run into all sorts of stuff. So is there going to be pressure? Yeah. These guys right here, though, they're very cold. Are they moving all that much? They're still moving, though. They still have, maybe they're not translating all that much, but I mean, they still are moving a little bit. So the rule about Charles' law is these guys are not going to need very much room. So if this was like, say, a balloon, these guys here, they're pinging all over the place. They're going to push outwards and they're going to try to expand this thing. These guys, they're moving, but I mean, it's like 6 in the morning. And they're having a hard time getting going. Does it need as much volume then? I'd say no. Then these guys actually require way less volume. In terms of analogies, it would be like all of us in this room here, we're okay. We have a lot of room in this room here. But then I hype you guys up all on energy drinks and sugar drinks. And you got to get moving, right? Do you really want to be cooped up inside this room anymore? No. So then I say, class, we're going to go outside and go play in the park. Because you need to spread out, right? So the rule here is as the temperature increases, the volume increases. Or as the temperature decreases, the volume also decreases. Does that make sense? rule about temperature. What units do temperature have to be in? Have to be in Kelvin. Okay, so here's today's law. We can actually put it all together. It's called the combined gas law. This right here is Boyle's law. PV equals PV. And this right here is Charles' law. V over T equals V over T. So we put it all together, it's called the combined gas law. These are very easy to know when you're using the combined gas law because there's like 5 variables. Because you need to know like a pressure, a volume, a temperature, a new pressure, a new volume, and you look for a new temperature. So long as you know how to do math and you can rearrange stuff algebraically, it's actually pretty easy. So let's do 2 examples. You've got a syringe. The syringe was 150 milliliters, but you squish it in. So now it's only 65. In doing so, the temperature of the gas went up. So the molecules got squished in, they started going a little bit faster, so the temperature went up about 2 degrees. Well, we used to have 105 kilopascals. What's the new pressure? So here's how I know it's the combined gas law. There are a lot of numbers here. When you see like a ton of numbers, it's probably the combined gas law. So pressure 1, volume 1, temperature 1 will equal pressure 2, volume 2, temperature 2. Start plugging in some numbers. What was our first pressure? Yeah, 105 kPa. I'm really going to recommend write in your units. It's worth the investment, at least at first. I know in my physics class sometimes I start skipping those once in a while, but like at least when you start out, get in the habit of it. It's worth it. Initial volume was what, 150 milliliters? You can convert it to liters if you want, but if you use your units correctly, they should cancel. The temperature was at 21 Celsius. We need that in Kelvin though. Thank you. 294 Kelvin. Okay, afterwards we don't know the new pressure, but we do know the new volume will be 65.0 milliliters. And 23 Celsius must be 296 then, right? Okay, how do you get P2 by itself? What's the math algebraic skills you need? Perfect, yeah, times up the 296, divide out the 65. So it would look like this. 105 kPa, 150 milliliters. This guy is now up top, so your 296 Kelvin's up top. You would have had 294 Kelvin down there, but now the 65 milliliters is on the bottom. That's pressure 2. The reason why I want you to focus on units is most of these units don't matter because that Kelvin will cancel with that Kelvin. This milliliters will cancel with this milliliters. So what's left? kPa. Here's the only twist. If this is in kPa, this one's in kPa. But like you can't have this one be in liters and that one in milliliters. You can't have this one in Celsius and that one in Celsius. Like everything has to be in the same units. The only for sure unit though is you have to have it in kelvins. You can't put it in degrees Celsius. Do you guys remember why we have to have it in degrees Kelvin? Sorry, you go first. Yes.
What do you put down if it's at a constant temperature?
You don't even worry about it. If it says it's at a constant temperature, we can actually cancel this temperature on both sides out then. So then it's just PV equals PV. Does that make sense? That's a good question actually. If something ever says the temperature is constant, it doesn't give you a number, then if this number is the same as this number, you can actually cancel them out. Good. Sorry, back to my original question there. Why does it have to be in Kelvin? Driana, what did you say again?
Because it starts at 0?
Yeah, we have to start at 0. Otherwise, if you use Celsius, you might get negative numbers. But like, you shouldn't really have negative temperature. Because you can't have a negative volume, you can't have a negative pressure, you can't have a negative distance, you can't have a negative, and all that stuff, right? Well, why can you have a negative temperature? Well, really, you shouldn't. We have negative temperatures, though, because negatives kind of imply that it's really cold, it's below 0 in Celsius. Okay, math. Do you guys get an answer? 244? You got to be really careful here. Make sure that when you do this, you do all 3 numbers in brackets on the top, and then both numbers in the bottom in brackets as well. So say that one more time. What'd you get? 244? Anybody else get that too?
Yeah, I got that.
Okay, good. Okay. I told my chemistry 30 class the other day that I always make sure I ask people more than once. There was one example I did a few years back where we did like 3 whiteboards worth of work and we got the wrong answer and we couldn't figure out why, and it was like the very, very first number. I asked someone to do a quick calculation on their calculator and they totally screwed it up. And so like all of our work was completely wrong because I asked somebody, hey, do the math, and they did like a small error. So, not that I don't trust you, but it's always good to check. That's it. I'm done. I mean, seriously, that is it. Like, that's the law. Okay. So here's what I want you guys to do for the rest of class. You have an hour. Use this hour plus whatever you do tomorrow to reinforce this, practice it so you get pretty good at it. I got a bunch of examples here. I also gave you guys a practice sheet here. This is not due. I'm not going to mark it unless you want me to. But hopefully you get the point. I mean, it's good because it will help you get better. That makes sense? If you want to, you could even start working on your assignments more too, because you can probably do a bunch of questions on the assignments already. But for the next hour, do something to enhance your learning somehow, whatever it is. Take a break if you need to. I'll still let you do that. Call me over as you need. But I want to give you guys time to do stuff. So do stuff.
So, quick question.
Yes.
Constant temperature.